Welcome to the lecture 13 of Logic and Distributed Control System. So today we are going to discuss about PLC arithmetic functions. Last class we have discussed about the PLC counter functions. So objectives of this lecture is that at the end of this chapter you will able to add and subtract numbers using the PLC add and subtract functions, explain and demonstrate how PLC handles overflow and negative numbers for the add and subtract functions accordingly, and explain the programming, operation and utilization of the repetitive clock. Then multiply and divide numbers using PLC multiply and PLC divide functions. Find square roots by using PLC square root function. Describe other major PLC trigonometric and log functions. Describe other major PLC arithmetic functions. Apply arithmetic functions to process control operations. So as an introduction, most PLCs have basic arithmetic functions designated as math functions. These basic functions are add, subtract, multiply, divide and SQR, which is indicated by square root function. Large capacity PLCs have an extended number of advanced arithmetic functions. So as we have said that we are going to understand about the basic functions, that is add. So we will start with PLC addition and subtraction. So now the figure shows the PLC add function. So this is the format, block format through which we can perform the addition operation. So here you can see that one enable switch IN65, and in the format three registers are there. One is operand 1, which is indicated by input register 0062, and then operand 2 may be the HR0041, may be a constant, and the addition operation will be stored in the output register OR0013, which is indicated by destination register, and this is an addition operation which is indicated by this coil AD0078. Okay, so now we have to understand how it is going to work. Now here that figure it adds only when the enable line changes from off to on. So here it is normally open, so when it is closed then it is going to on. So now the addition operation is enabled. Now how it is going to add? When enabled, the numerical value in the operand 2 register is added to the numerical value in the operand 1 register. The resulting value then appear in the destination register. So the operand 2, the whatever the content of the HR0041 will be added to the content of IR0062, which is the operand 1, and the addition operation will be stored in the whatever the result, that will be stored in the OR0013, which is the destination. Okay, so here another format has been shown, that is the multiple coil format, but as I said that we will follow this block format for the development of ladder programming. Fine. So here the coil function, the figure B shows the another format that operates similarly. The two numbers to be added are entered in the location 30 and 31. So this is the 30 and 31, where you can see that 87 and 92, these are the numerical values are placed in the registers 30 and 31. Then the result in the addition then appears in the location 32 when input 1 to 1 is energized. So whenever the 1 to 1 is energized, so then the result 179 is going to be stored in the register 32. So you can add more than two numbers using one function. Otherwise you would have to add two numbers and then add the third to the result, requiring two lines of program. So if we want to perform the two addition operations, so we have to take two blocks. Now here we have to understand what is the function of this coil AD0078. Previously for the counter and timer we have observed that the coil is going to be energized whenever the accumulator value is the preset value. So here we have to know what is the function of or how the coil is going to be energized AD0078. But here most important thing is that by AD0078 you are indicating that this particular format is for the addition operation. So this is very important to develop the ladder logic. Whenever you will be asked to develop the ladder logic using this mathematical operation or any other functions of PLC, then this format is important. So you have to strictly follow these formats. Now here you can see that before enable, so whenever we have a addition block or adder block, so now in a operand 1 HR75 we have a number that is 462, in operand 2 that is HR0076 having another number that is 0327, and then this is the destination that is HR77. So before enable, the HR77 can contain any value, and at that point of time AD0030 is off. Now when it is enable, so after enable what will happen, the HR75 is still holding the number 462, HR76 is still holding the number 327, but HR77, the content of the HR77 holding register 77 is going to change with the result of this addition, that is 789, which is indicating the sum. But after doing this operation, still the AD30 is in an off position. It is not going to change its status. So when this AD0030 is going to change its status, only when there is an overflow. So suppose we are assuming that the 10,000 is the maximum value the addition can be held by the addition result can be held by the destination register. So then if we have a number 9642 and then we have a number 3471, then after enable we are finding that the result, sum result is 13113, which is greater than the 10,000. Then what will happen? The HR77 will contain 3113 because 13,113 minus 10,000 is 3113, and at that time this AD0030 is going to be on from the off position to indicate that there is a overflow. Otherwise, for the normal operation, this AD0030 having no activity, only you have to indicate the AD0030. This AD indicates it is an addition operation. Okay, that's all. Now, after knowing this format, what will be the application of this addition operation? So we will create a situation such that you can understand how this addition operation is important in industry. Suppose two conveyors fed a main conveyor. So then suppose this is the situation. So two conveyors we have. So feeder conveyor A and feeder conveyor B, and we ultimately it is having a main conveyor. Then what has happened? Something like this, that is the main conveyor count is determined from the count of parts entering from the other two conveyors. So we want to know how many numbers of parts are going through the main conveyor, which is coming from the two conveyors, that is A and B respectively. But the count on each feeder conveyor is determined by a counter. The counters on each feeder conveyor are input pulsed by a proximity detector once for each part leaving the conveyor. The count of total parts entering to the main conveyor is then determined by adding the two feeder conveyors counts using the add function. Okay, because somehow the some reason this main conveyor we are not able to install any counter. Okay, so we have the facility only that feeder A having a counter. Suppose here one sensor has been placed such that whenever the parts is going to pass, one pulse will be created. So similarly for the feeder B also there is a sensor. Whenever a part is going to pass, a pulse will be generated. So now we want to know how many numbers how many parts are going through the main conveyor by counting, first we have to count the feeder, the number of parts in the feeder conveyor A and the number of parts in the feeder conveyor B, and after that we have to add, because we do not have any facility to count the number of parts in the main conveyor. Suppose this situation has happened, so for some reason we cannot get the main conveyor to make a count. Fine. So how we can develop the logic? Here you see the part of the program has been shown. We can have the operand 1, which will be the accumulator, which address of the operand 1 will be the address of the accumulator of the counter 1, and HR42, which will be the accumulator address of the counter 2, and then we have the destination register HR0043, where we can get the total count which is passing through the main conveyor. Here I will show you the entire programming, then you can understand. Here you can understand what is the need to have the proper addressing of the registers. Okay, that you can understand. So, and another thing is that every 30-second interval of time we want to know, what is the total number of counts in main conveyor, and we can have the printing facility also. Okay, so so how we will develop? So now we can understand that here one thing is important, that we have to first count the how many number of material or the parts are going through the conveyor A, and the count must be placed at HR41. Okay, so now we know that there is a format for the counter, that is we can write this is the count. Okay, and another. Okay, so here you remember that you have the preset value. So preset value, what will be the preset value of the counter 1? We can keep very high value. We don't know how many number of parts are coming, so we will keep any high value. So suppose it is IN01 and IN02. Fine. And here there will be a counter address, so it is a up counter. Okay, and what will be the format for the counter? So here you can see that that is, you can say that UC17, up counter UC17. Okay, and here very important thing is that what should be the accumulator address of the counter 1? There must be that HR, what will be that? It is HR41. That is very important. Okay, fine. And then we can have another counter. Okay, that is suppose IN03, that is the count. Okay, so where the IN01, so IN01 is receiving the pulse from the sensor which is placed in the conveyor A. Okay, so similarly IN03 is can be designed. Okay, so here also you can have the preset value high, but here most important thing is that its accumulator register address will be HR42, because this is going to be stored in the adder 1, means in the adder that is operate as a operand 2. Okay, so now here another so it is up counter 18. Okay, and now you can have the use of timer also, because at 30-second interval of time we want to know that what will be the value of the count. So at every 30-second interval of time we have to enable the adder circuit. So what we can do, we can have, so here you can have the same address IN02 also. When these two are close, then both the counter will be energized at the same time. Okay, so now how you can generate the pulse at every 30-second interval of time, that we have understood from the timer operation. So suppose here one timer we are taking. Okay, and this is the timer address. So timer, how we can have the timer. So this is the suppose T13, okay, and here we will make it normally close, that is address is T13, and this is the run, and the preset value we have the 30 second, okay, and you can give the HR01 maybe for the timer, okay. Now this T13 will be the enable. So now next line what you have to write, you have to write the, so this is the enable for the adder, okay. So then you can write this one as T13. So every 30-second interval of time it is going to be closed, and then rest of the things will be same, that is AD whatever is designed here, that is AD67 you can write, okay. And mind that here this operand 1 will be HR41, operand 2 will be HR42, and destination will be HR43. So every 30-second interval of time, whatever the count, that is going to be. So here you can give IN04, okay, whenever IN04 must be closed during the operation of timer, okay. So in this way you can develop a complete ladder programming where you can lead or you can solve this kind of situation, okay, or you can deal with this kind of situation. Now we are going to understand the subtract operation, okay, how the subtract operation can be performed using PLC. The PLC format for subtract is same as for add, and the function operation is similar. For subtraction, operand 2 is subtracted from the operand 1. The result is found in the destination register, and figure shows the subtract operation. So here you can see that similarly the enable line is there. This is the operand 1, this is the operand 2, and this is the destination, and the subtraction operation is indicated by SB, and then address is 63, okay. Similarly, when you are going to subtract, then suppose HR132 having a value 8642, and then HR133 having 6218, then HR134 may contain any previous value. When the this is the before enable, whenever you will enable, then subtract operation will be done, and the result 2424 will be stored in the destination register, that is 134. And this SB0063 is going to be energized only when if you have a negative number, means when the operand 2 is greater than the operand 1, then only you have the negative number, and that condition the SB0063 will be energized, okay. So this is the means this is the way the subtract operation is going to perform. And application, the same way the adder operation what we have shown, the application can be shown for the subtract operation. That suppose we want to know that how many number of parts are going through the conveyor B, but in this case what has happened, the counter is available to be installed in the conveyor A, means conveyor A as well as the main conveyor, but somehow we do not have a facility to place the counter in the conveyor B. Then if I want to know the how many number of parts are going through the conveyor B, then what we can do, that the number of counts what we are getting through the main conveyor, okay, and whatever the counts we are getting in the conveyor A, that must be subtracted from the value in the main conveyor. So this way we can have the count how many numbers or how many parts are going through the conveyor B. So now here that has been discussed, that in this example the output count and only one input count are available. One of the conveyor inputs is not accessible for some reason. To obtain the input B count value, subtract the input A count value from the output count. The result is the B conveyor count. The count is again determined by a 30-second counting interval. The count is taken for 30 seconds. After and then reset to 0. Again, initializing is needed periodically for accurate operation. Initializing figures are initial numbers of the parts on the conveyor A into the counting results. So similar way we can develop the programming what we have developed just in the last example. Okay, so here the last line has been shown. So here the counters are not shown. So full programming you have to develop. Okay. Now PLC operation with set points and tolerances. So now another example where you can see that adder and subtractor operation, or this adder and subtractor we are going to use together to handle this kind of situation, that PLC operation with set points and tolerances. One useful function of the add and subtract function is to set range. For example, there is an inspection system with periodically changing base dimension and periodically changing the tolerances. So we know that if we have a base dimension x, and suppose tolerances is plus minus y, and this x and y is changing periodically. So now if we want to know that what is the result, that x plus y and x minus y, to know the particular measurement, then we can take the help of this addition and subtraction operation of the PLC. The PLC can easily and quickly reset the dimensions and tolerances. The preset dimensional values are transmitted to specified PLC outputs. These output values are used to set the positions of an automatic gauging system. In example, the base dimension, suppose, or the set point is set at 6.250 inches, and the allowable tolerances are chosen for these illustrations are plus 0.25 and minus 0.035 inch. And here the graphical representation, suppose we have a set point of 6250 mil. Here you see 1 mil equal to 0.001 inch, and we want to know for a perfect gauging that after adding the tolerance, that is plus 25, what is the value, and by subtracting minus 35, what will be the value. Okay, so this is the tolerances, plus 25 and minus 35, and this 6250 minus 35 25 can change periodically. So how we can do that one? It is very easy to do. That figure shows how the setting can be accomplished by programming a PLC. For 3 externally fixed values, a PLC is not needed, but if it is periodically changing, then it is needed. Our system is valuable when the dimensions are varying quickly as production varies. The set points are entered into HR001. So let us see. So here you can see that operand 1, operand 2 for the first we have used a adder, and another subtractor we have used. The address of the operand 1 for the adder and subtractor are same, and but the operand 2, the address of the operand 2 of the adder is HR002, and the operand of the observer the subtractor is HR003, and the destinations are also different. So what should be the operand 1? Operand 1 for both the cases, it will be the base value, that is the 6250 or set point value, and the operand 2 for the adder will be the upper tolerance, and the operand 2 for the subtractor will be the lower tolerance. Okay, and once you will enable it, then what will happen? Then you will find that the HR004 will contain the upper limit, and HR005 will contain the lower limit after the subtraction. Okay, so in this way, and easily that we can change the operand 1 and operand 2 for the adder and subtractor based on the requirement. If the suppose periodically this operand 1 and operand 2 are both the cases, addition and subtraction operations are going to change, then we can take the help of the PLC. Okay, so this is the way we can handle the situation using adder and subtractor. Another important thing is the PLC repetitive clock. Suppose here we have observed that for the adder as well as the subtractor, that whenever this CR127 is going to be on, then only the addition as well as the subtraction operation is going to be performed. Suppose we want to develop a automatic enabling circuit for the adder and subtractor depending on the scan time of the PLC. Okay, so now here you can see that the add and subtract functions discussed so far in this chapter do not usually operate continuously. They only perform the addition or subtraction operation once the function is enabled. If enable remains on, nothing else happens even though the operands change. When enable is off, nothing happens either. Therefore, a repetitive on-off enable is needed for continuous operation. Figure shows a repetitive clock arrangement. A coil turns itself off and on at every fast rate, that is about 2 times of the scan time rate. Here this is the circuit. So here you see CR43 is a normally closed, and a coil we have taken, that is CR43, and then CR43 as a normally open is taken as a enable switch or enable contact for the adder as well as the subtractor. So now how it is going to work. Now the sequence for the repetitive clock is this. On the first scan, the relay coil is turned on through its own contact. When the coil goes on, it opens its own enabling contact, which is normally closed. So whenever the first scan, the PLC will see that CR43 is closed, so CR43 will be energized, and once this CR43 will be energized, then CR43 is as a contact which is going to be false. At the end of the first scan, the CR43 NC contact is updated and opened, and the next scan. So next scan, what will happen? This CR43 is status of the CR43 will be updated. At that time it will be open, and if it is open, CR43 is going to be off. Okay, so on the next scan, the coil is turned off. Update at the end of the second scan. Whenever the second scan is going on, again it will be reclosed, and the self recloses the self enabling contact. The process then repeats itself continuously. So in this way, depending on the scan time, you can make the enable periodically for the adder and subtractor circuit or the block. So the next is the PLC multiplication. The multiplication format is similar to the addition and subtraction formats previously discussed. Figure shows the multiply function. The operand 1 assigned a register number. Okay, so here this is the format. So MP representing the multiplication. So operand 1 is the HR037 and operand 2 is the IR081, maybe constant. Okay, and the total results will be stored in HR0068 and it may be two registers, that is the HR68 and HR69, because for the multiplication results will be bigger, so we may require total 8 bit of two registers, that is if we will assume that each is 8 bit long, so then 16 bit may require. Okay, so operand 1 assigned a register number, operand 2 can be another register or it may be a constant. The result of the multiplication appears in the destination when the function is enabled. The destination is two registers wide by necessity, so multiply 34 by 86 would require only one register, that is 4 numbers wide, that is answer is 2064. But however, if you want to multiply 6453 by 8933, you have the result 57644,649 would require 8-bit wide slot for two registers to accommodate the answer. The multiplication takes place only when the enables comes on. Normally, the coils comes on when the multiplication is completed. The coil on-off has no numerical significance as it did in add and subtract operation. Okay, so this is the way the multiplication is going to be performed. What is the application? A simple process application for counting the cartons as shown in the figure. So here suppose we have to know that how many number of cartons are going to pass, such that we can understand that total number of bottles inside the, means the total number of bottles is packaged during the operation. How? Now suppose the count from a carton counter enters the PLC and put into IR001 and then into operand 1, that is and then into operand 1. Each carton contains suppose 12 bottles, therefore 12 is inserted as a constant in operand 2. So now if we want to calculate that number of bottles, and if we know that how many number of cartons and each carton contains of 12 bottles, then we can understand or we can count the number of bottles. So to keep a constant count of bottle, the PLC would constantly multiply the carton count by 12. The destination register, that is HR001, will show the number of bottles output each time the function is enabled. A number of these multiply functions could be combined to give a total planned unit output. Means in a day, suppose if you want to know that how many number of bottles are packaged, the constant in each function would be bottles per carton and that particular count. So suppose here that operand 2 is 12, and then a PLC addition program of all individual counts would then give the total plant bottle count. So in this way we can use the PLC multiplication function. So now we will come another application of this multiplication, that is the squaring. This is normally no squaring function in a PLC. Squaring is simply a matter of putting the numbers to be squared in the both operand 1 and operand 2 of a multiply function. The square of the original number then appears in the destination register. So the same value we will put in operand 1 and operand 2 to get the squared numbers or the squared result in the destination register HR06. Okay. Now we will discuss about the PLC division. The division function which is shown in the figure is similar to the multiplication function. Here is the format. So operand 1 HR33. So it may be two registers, that is HR33 and HR34. And operand 2 is HR61, may be a constant, and destination is represented by OR13. Fine. Now the division function is how it is going to perform. Operand 1, the dividend, and is divided by the operand 2, which is the divisor. The numerical result of the division appears in the designated register when the function is enabled. Again, the division takes place only at the time enable is energized. To facilitate division, operand 1 is a 2 registers wide and the operand 2 is only 1 register wide. Operand 2 may be a registers or a constant numerical value. A numerical example of a division is shown in the figure. So here is the suppose division operation is going to be performed. That suppose 648 127 is divided by 2421. So the operand 1 will be stored, the operand 1 is containing this value and operand 2 is containing this value. Now really if you do the division, the result is in a fraction, that is 267.71045. So now how the division operation is performed by the PLC. Now you will find that actually the operand 1, that is the 648 127, if you multiply by 267, we are getting the result 446 407. Why we have multiplied by 267? Because you are finding that the result, the integer result is 267. So that's why it has been multiplied. So result is 646 407. If you subtract, the result is 1702. So you will find that the integer what you are getting, that is correct. It will be stored in the destination register, that is 267, but the it is not going to have the decimal values. Instead of that, this subtracted value 1702 will be the result. Okay, so if you want to get the correct decimal results, then again you have to do the division by 2421. Okay, so this is the way the division operation has been done. So here dv is the indication that it is meant for the division operation. So what is the use of different division operation? Now for an example of scaling by division, so an analog measurement numerical value is inches and you want to convert it in feet. Yeah, so that's why this inches value is fed into a PLC register and the measurement value is transferred, which is not shown in the diagram, within the PLC to the register HR078. So later on we will see how to feed these numerical values to the registers, that we will see. Okay, so move operation, when we will learn, then we will understand how to move it. So the measurement value is transferred within the PLC to register HR78 and HR79, which is a two registers wide, and to divide it by 12, because we know that 1 feet is equal to 12 inches. So to divide it by 12, put this constant to the operand 2. This divisor could also be a fixed or variable value put in a specified register. The resultant division of value is going to appear in the two output register, that is 124 and 125. The remainder appears in 125. The remainder is a whole number. It is not a decimal value, as just now I have indicated in the previous example. To convert the remainder to feet, another division process is necessary. If the required output accuracy is less than the whole feet, convert the remainder into the decimal form. This would be accomplished by an added program step. What is that? Divide the numerical remainder in OR 125 by 12 and place the result in another output register, for example OR 026. 126. So this is the way we can do, that is the operand 1 contains the value for which you want to convert it in feet, and an operand 2, that is 12, which is constant, and destination will contain the division operation, which will be converted in the feet. Then PLC square root figure shows the square root function found in the PLCs. So this is the SQR is reserved for the square root function. The number whose square root we are going to determine is placed in the source. The source input number is contained in two registers, so that it may be up to this high value. When enabled, the function calculates the square root and places it in the destination. The destination is one register wide, that is 9999 in value, and there is usually no remainder registers. Okay, and also you will find that PLC contains some trigonometric and log functions also. A number of functions perform trigonometric and logarithmic operations in general in mid-sized PLCs. A general block functions for this shown in figure. So here the source and here is the destination, and here the output, and output will be coded by the function designated. Okay, a general block function, that's why it has been shown. The input going from off to on causes the mathematical operation to take place. The source register's value is analyzed appropriately and the calculated value appears in the destination register. The angle involved in trigonometric functions are normally stored in radial, and there are upper limits on how big a number the log functions will handle, as listed in the operating manual. Okay, and these are the some special trigonometric and log functions will be performed by the PLC. Find that arc function, which is symbol by ACS. Okay, arc, sine, then sine, all these functions can be performed, and other PLC arithmetic functions can be performed also. They are the average, file, negative, standard deviation, x to the power of y. All these functions also can be performed using arithmetic functions of the PLC. So I will stop here by summarizing that what we have discussed today. Mainly we have seen that how the addition operation and subtraction operation can be performed using PLC with example. Then we have understood the multiplication and division operation using PLC, and also we have seen some examples where these functions will be essential to get the results. Thank you.